At the precipice of a new era of computation, we are witnessing a revolution of intelligence. Yet, this entire digital architecture is defined by an invisible and lethal adversary: waste heat. It is the silent shadow of every calculation. The foundation of modern artificial intelligence no longer rests on software alone, but on a growing physical crisis. We have reached a thermal tipping point, where the heat generated by silicon begins to outpace our ability to remove it. The global demand for faster, denser computing has pushed AI rack densities past unprecedented thresholds. What was once a manageable challenge has evolved into an engineering battlefield, where every watt of power creates a massive thermal burden. As individual racks now surge past 100 kilowatts, the very air we have relied on for decades is failing. At these densities, air molecules lack the mass and velocity required to strip heat away from high-performance chips like the Nvidia Blackwell. Traditional air cooling solutions, the massive fan walls and sea-crack units of the past, have reached their absolute physical limit. They are effectively struggling against the sheer concentration of thermal energy, consuming more power just to move air than the servers themselves. To survive this crisis, we must look beyond the confines of air. We must return to the fundamental laws of thermodynamics to find a medium capable of handling the next generation of compute. The answer has been with us all along. The solution lies in the most abundant substance on our planet: liquid water. In the hierarchy of thermal management, water is not just an alternative. It is a superior physical inevitability for high-density environments. Comparing the volumetric heat capacity of air versus liquid reveals a staggering, non-linear difference in efficiency. It is a comparison between a gentle breeze and a tidal wave in terms of energy transport capability. Water possesses a volumetric heat capacity over 3,500 times greater than air. This means a tiny stream of liquid can remove the same amount of heat as a massive, turbulent gale, making it the perfect medium to manage AI's extreme and localized heat loads. This thermodynamic superiority is the cornerstone of the next generation of data centers. It is driving a radical shift in architecture, moving our most powerful machines away from traditional warehouses and towards aquatic environments. By turning to nature's inherent cooling mechanisms, we are solving technology's hottest problem. We are moving from fighting physics to utilizing it, leveraging the planet's natural thermal reservoirs to sustain our digital future. From the crushing depths of the deep sea to the glacial temperatures of the Arctic fjords, the Earth offers vast, untapped cooling resources. These environments provide a constant, low-temperature heat sink that requires almost zero mechanical energy to maintain. Experiments like Microsoft's Project Natick have proven the viability of this vision. By deploying hermetically sealed compute modules directly onto the seafloor, we utilize the constant chill of the deep, where the environment itself acts as a massive, passive radiator. In the north, frigid fjords provide a limitless supply of naturally cold water. By utilizing deep water intakes, data centers can achieve a power usage effectiveness of nearly 1.0, drastically reducing the energy overhead that plagues land-based facilities. However, integrating high technology with raw nature presents a new set of complex engineering challenges. Maintaining operational integrity in a harsh underwater environment requires expertise that bridges the gap between IT and marine engineering. In aquatic environments, engineers face a relentless biological force: biofouling. This is the persistent colonization of cooling surfaces by marine organisms, barnacles and algae that can rapidly congest the vital arteries of a cooling system. The expert solution lies in advanced ultrasonic anti-fouling technology. By using high-frequency cavitation, we create a microscopic barrier that prevents biological attachment without the use of toxic chemicals, keeping the heat exchangers pristine and efficient. Coupled with specialized titanium alloys and anti-corrosion coatings, this technology ensures that nature's cooling power is harnessed reliably. We are building systems designed to survive and thrive in the most corrosive environments on Earth for decades. In this new paradigm, the heat produced by AI is no longer treated as a waste product to be discarded. It is recognized as a vital, high-grade energy source that can be repurposed for the benefit of society. Thermal exhaust, once expelled uselessly into the atmosphere, can now be channeled and recovered. By utilizing heat pumps and district heating networks, we transition waste heat from a liability into a valuable asset for urban infrastructure. Imagine data centers evolving from power-hungry sinks into the thermodynamic hearts of the future, pumping warm energy into greenhouses, homes, and offices, creating a symbiotic relationship between compute and community. By embracing the deep blue compute, we do more than solve a thermal crisis. We establish a circular economy where technology and sustainability exist in perfect harmony, powered by the very laws of physics that once threatened to limit our growth. Thermalops, mastering the heat of intelligence.